Hello there, ATSEVS113 students. Dr. John Schrage here, and I want to do a lecture about winter weather. It's Christmas time when I'm recording this, and we got the house all bedecked in Christmas trees and Christmas lights and stockings and so on, and that got me thinking that it's time to refresh the lecture about winter weather. And as it happens, there's no single part of your textbook that's about winter weather. There's not a winter weather chapter. It's kind of scattered throughout, but we'll kind of rake together things that happen in your textbook and kind of fill in some gaps to talk about the business of winter weather. When we're talking about winter, first off, we have to know what time of the year we're talking about. We need an actual definition of it. And it turns out there's a number of different ways that you can actually define the period of the year that you're talking about when you talk about winter. The one the public always seems to latch on to is what is technically called astronomical winter, and that is the period between the December solstice and the March equinox, so between approximately December 21st and March 21st. And that is not without its reasoning. You're going from, they're saying then the winter is the period of the time from the shortest day of the year in the northern hemisphere to the time of the year, the equinox, when the days are 12 hours and the night is 12 hours. That's not an entirely stupid idea, except is that really how you think about winter? That winter is like the period of time where the days are short but getting longer? That's exactly what my 6-year-old was told in first grade the other day, is that winter is the period of time when days are short but getting longer. That doesn't really ring true to me. I think the meteorological definition of winter makes a lot more sense. The meteorological definition of winter is the period of time of the 3 months of the year that are coldest in the northern hemisphere. So the definition that meteorologists tend to use is that it's December, January, and February. And I think that's most people's intuition. I mean, do you think of December, early December, as being fall? I mean, it's winter. So even though that isn't the definition that people tend to use in their day-to-day life, it is actually a very useful way of defining what we mean by winter. Now, just because that's our definition of winter, and we can picture in our mind what winter weather looks like, doesn't mean that there can't be winter weather outside of winter. For example, you are connected to Creighton University in Omaha, and you're probably too young to remember the Halloween storm of 1997, a very famous blizzard and ice storm that wiped out power to much of the city of Omaha for over 7 days. There was a lot of ice and a lot of snow. The leaves were still on the trees, and when the snow and the ice stuck to the leaves, it pulled the branches down, took down power lines. They had to cancel. The storm itself was a few days before Halloween. It was on the 28th or something. But there was no way the kids could safely be outside with power lines down and so on. A famous storm that is still talked about in textbooks and so on. Another example of another really good example of a storm that is famous for being a winter storm is the so-called perfect storm. You might have either read the book by Sebastian Junger or seen the movie with Mark Wahlberg about the perfect storm. But this was an enormous cyclone that famously brought big winds and big gusts and so on to the North Atlantic and resulted in the loss of a bunch of fishing vessels, but also dumped enormous amounts of snow across the upper tier of the United States, and it was mid-October or something like that. I mean, it was not inside of winter. Another good example of a winter storm, a major winter storm, a history-making winter storm that happened outside of the period of winter, is the so-called Storm of the Century, which happened in 1993. This was March of 1993, March 13th. This brought well over 20 inches of snow across a big part of the eastern United States. Parts of northern Georgia and south and North Carolina got over 40 inches of snow. This was a giant nightmare. I'll tell you a story about the storm of the century. I was actually a student in college, grad school actually, when that storm happened. And I was on spring break when it happened, and I happened to be taking my spring break visiting friends who lived in D.C., and this was a well-forecasted storm. We knew that the storm was coming, and I actually got an early flight to get out of there. But, you know, D.C. was basically shut down for several days afterward. I don't remember officially what the Washington, D.C. area got, but something, you know, like 20 inches of snow. I mean, this was a very famous storm that had a number of very famous impacts at the time, but it's getting to be a long time ago. Of course, when we're talking about winter weather, you talk about cold, and you talk about the messy forms of precipitation. And let's dwell on the messy forms of wintry precipitation first. Broadly speaking, winter precipitation falls in 4 forms: snow, sleet, freezing rain, and rain. Now, rain may not be something you immediately thought of about winter, but you know that it rains in the winter, especially farther south. Rain can be an important part of the total precipitation that you get in the winter. And these four forms of precipitation are actually quite closely related. I mean, if you think back to, I think that's Module 3 in the course, where we learned about how like cloud droplets grow and so on, you remember that, well, you might not remember the details, but the key to the process of how precipitation happens in the mid-latitudes was the so-called Bergeron process, in which clouds have to be a mix of ice crystals and supercooled water droplets. Now in the summer you might think that's too warm, but actually even in the summer that works. But in the winter there's no doubt about it. The temperature up in the clouds is going to be below freezing. But the clouds are going to contain a large number of supercooled water droplets and some ice crystals. And the ice crystals grow by the Bergeron process while the supercooled water droplets shrink. And we end up with the heavy falling ice crystals. Now in the summer they always melt, but in the winter they may or may not melt, and once they melt they may or may not refreeze as they are falling. And so all of our precipitation frankly in the summer or the winter in places like Nebraska, but certainly in the winter all of our precipitation started as ice. The question is what happened as it fell through the atmosphere. We're going to need to know what the temperature profile is in the atmosphere in order to know what kind of precipitation we're going to get at the surface. And we're going to be working with a series of diagrams that look like this, where there is height on the y-axis and temperature on the x-axis. And I deliberately did not put a scale on either the height or the temperature. It's going to be the shape of the curve that we draw that is the profile of the temperature that's going to matter. We don't actually need to be like critically concerned about, is this the lowest 5 kilometers of the atmosphere? Is this the lowest 8 kilometers? I don't care. That's not what's important. We just broadly want to talk about, like, is it above or below freezing, which is why on the x-axis I did label 32 degrees Fahrenheit, 0 degrees Celsius, the freezing line. So if we want to talk about the kind of temperature profile that we're going to need to observe with like a weather balloon and a radiosonde and so on, in order to get snow, it's going to look something like this, where as the balloon was rising and it was measuring the temperature, it saw temperatures that were always below freezing. To get snow at the surface, you can't have had those ice crystals ever melt as they were falling. If they melt and are liquid, they're either going to hit the ground as rain or freezing rain, or they'll refreeze along the way, but that's not going to be snow, that's going to be sleet. So the profile has to stay below freezing through the whole depth of the atmosphere here. And to kind of illustrate what's going on here, see how along the side of that graph there I kind of have those little X, 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 X. I'm just showing the ice crystal as it falls. The symbol in meteorology for ice crystal is a lowercase x. And so I just, by force of habit, that's what I used here. So an ice crystal that's up there like by the letter S in the word snow is falling, 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 and you can see it went through all of its path all the way to the ground as the form of an ice crystal. I labeled it as an X all the way down. Now, in practice, this is there's a little bit of wiggle room here. You could have a small layer near the surface where the temperature is slightly above freezing, and you can still get snow. It probably will melt once it's on the ground, but you will still have wintry weather conditions where snow is falling. In fact, half of the time when the temperature of the surface of the Earth is at, the air at the surface is 36, there's precipitation, half of that time that precipitation will be snow. Although it never snows if the temperature at the surface is greater than about 41. After that, there's just no way the ice crystals, they're going to warm up too much and they're going to melt. Don't get me wrong, the ice crystals melt if they get above 32 degrees. It's more a matter of if there's a shallow layer near the surface where the ice crystals can fall through it pretty fast before they have a chance to warm up, they might make it to the ground in the form of snow. Oh, snowflakes, aren't they beautiful? They have such a fascinating, complicated shape that I love to teach about how that happens, but that's a 500 level class. I can give you some vocabulary words about how this happens and so on, though. Why they get that, the right word for that kind of shape, that kind of six-sided branched shape there, is that it is an aggregate. Because that's not a single ice crystal there. It is built up of it is aggregated a large number of ice crystals. But they grew. They grew there. It wasn't like collision and coalescence, like as the ice crystal fell, it hit other ice crystals and they froze on in that pretty pattern. No, they grew. But they are not a single ice crystal, they're a variety of different ice crystals, each of which occurring in a different shape called a habit. This is a weird word, this word habit. You've actually encountered this word one other time in your life. This isn't habit as in picking your nose is a bad habit. This is habit as in like what a nun wears. That outward appearance of a nun with the black gown and the white hood and things like that, that's called a habit. It's an old use of the word habit that means outward appearance. And habit is the right word that like physical chemists use for the fact that materials form crystals with different shapes. And in the case of water forming crystals in the atmosphere, there's actually a variety of different habits of ice that form slightly different shapes. A snowflake is a collection of these crystals, all with these different habits. Ice, when water vapor converts by deposition into ice on these ice crystals, it will form a different habit, a different shape, depending on exactly the combination of temperature and humidity and pressure and so on it's under. And so I'm going to show you some scanning electron microscope pictures of these kind of habits just to give you a sense of how bizarre they are. So like for example, this is a microscopic picture of a hexagonal plate. Hexagonal plates are one of about 20 known habits of ice. And again, keep in mind, this is a picture through a microscope. The little fuzzy stuff that's on the edge, by the way, there, that has to do with how in the lab they grew these crystals. That's not the thing. It's this actually perfect six-sided shape that's thin but wide that I want you to see here. That's called a hexagonal plate. Under a very specific range of temperatures, pressures, and humidities, when water vapor deposits into the form of an ice crystal, it makes a hexagonal plate. Or it can make another habit of ice called a thick plate. And again, this is just a scanning microscope picture. Again, some of the kind of weird coral-looking stuff around the edges and so on, that's just how they created this crystal in the lab. It's the perfect six-sided tall plate there that actually has these indentations on the side that's interesting. That is a known habit of water when it makes an ice crystal. There's even weirder ones. Here's a solid bullet. That is another habit of ice that forms under a very narrow range of temperatures, pressures, and humidities. And as long as we're in that range, ice forms in the form... Again, keep in mind, this is not something you'd see falling from the sky. This is going to be a tiny piece of a snowflake. Okay? But when the crystal is growing, if it passes through a part of the atmosphere that has just the right combination of temperature, pressure, and humidity, that part of the ice crystal will be a solid bullet. There's even more strange ones, like hollow bullets. I mean, how in the world is that even possible to get ice crystals like that? It's just a natural shape the crystals form under. That is a habit of ice. Here's another weird one called capped columns. Again, the corally looking stuff on there has to do with how they grew the capped column in the lab. But again, this is not something you're going to see falling. You're not going to catch one on your mitten and look at it and go, wow, capped columns. This is a microscopic part of an ice crystal, like of a snowflake. The snowflake is an aggregate of a whole bunch of these kinds of things. By the way, sometimes that little corally looking stuff that's on these crystals, this happens to be, by the way, another habit of ice called needles, where they form these long, thin, six-sided tubes. But that kind of coral looking stuff that's on the ice there is called rime. Rime is when supercool water droplets touch an ice crystal and freeze on. That is kind of like collision and coalescence was back in the third module. When the ice crystal is falling, if it hits a super cool water droplet, the super cool water droplet just changes into ice instantly, and it kind of forms that little ball of ice on the edge of the ice crystals there. And so that is an example of rime. I don't know where that word rime comes from, but you're going to see that word rime come up again later in the lecture. This actually gives us, this idea of all these habits of ice actually explains why no two snowflakes are identical. Once an ice crystal starts to grow by deposition of water vapor in the atmosphere, it is going to be following a path through the cloud, either just falling or maybe going up and down in the course of updrafts and downdrafts or whatever. But no matter what, it is experiencing a range of temperatures and pressures and humidities as it follows a complicated path through the cloud. And so as it is growing, for a while, let's say maybe it's hexagonal plates, and then it'll hit another part of the atmosphere where the right habit to be growing is, let's say, columns, and it'll start growing columns on the end, each of the 6 ends of the plate, and then maybe it'll hit a part of the atmosphere where the right combination of temperatures and pressures are that it's growing bullets, and so maybe bullets will start growing on the sides of those columns, and you get a weird aggregate of lots of different shapes if you look at those ice crystals under the microscope. And no two snowflakes will have followed exactly the same path through the cloud, so no two snowflakes will have encountered exactly the same combinations of temperature, pressure, and humidity, and as a consequence, they will always look different. In a lab where you would have very precise control of the temperature, the pressure, and humidity, and you could be growing these ice crystals to look at under a microscope, you can get crystals that are indistinguishable. But in the natural world where they're all blowing around in a cloud and following their own complicated path as they fall, it'll never happen. You would never find two snowflakes that are exactly the same. What you also won't probably find very many of if you go outside and you start catching snowflakes on your mittens is ice crystals that are whole, that haven't fragmented. Very few ice crystals make it all the way to the ground without breaking or fragmenting. Here's an example of such a thing where one of the 6 branches of a snowflake fell off. In and of itself, that's probably not terribly surprising. I mean, they're tiny little flakes of ice bumping into anything, or just even the temperature stresses of like maybe one end of the snowflake being a little warmer than the other can can break it apart. Just a tiny little temperature shock. But here's the deal. It's actually quite important that the ice crystals can do this. There are some, when we learned in Module 3 about the precipitation and how ice processes happen inside of a cloud and Bergeron processes and so on, we glossed over a lot of the details. And one of the details are you need a lot of ice crystals in your cloud to get the Bergeron process going. And the truth of the matter is there aren't usually all that many to start off with. But here's the deal. If you take the ice crystals you've got and you break them, you now have more ice crystals. Okay? It is the actual number of them that matters. Like there are 300 ice crystals per cubic meter is so much better than having 30 ice crystals per cubic meter. So if you can take each ice crystal and break it up into 10 pieces, you now have 10 times as many ice crystals. That is actually an important detail buried in how the Bergeron process works that we're not going to get into, but it actually turns out to be important. It's not sad that the ice crystals break up. It's actually necessary to how the precipitation forms. Related to snow, before we move on to our other forms of winter precipitation, related to snow, there's a really cool phenomenon called Graupel. Graupel also is known as snow pellets, and Graupel are these soft little balls of ice, and they're really bright white, but if you pick them up off the ground, they're squishable. You can crush them with your fingers. They're like little snowballs, and they are actually made in the atmosphere when a nice snowflake is falling from the cloud and it moves through a layer of supercooled water, and the supercooled water rimes on. It's like a collision and coalescence type process for a snowflake. So the snowflake is falling, it hits some supercooled water droplets, and they start freezing on. And it kind of just sort of makes this crusty little ball of ice. I mean, in theory, I suppose if you could kind of pick it apart with a scalpel, you might even find some remnants of the actual snowflake still inside there. But basically, it's a little snowball. It's bright white, and it's soft. And you don't see them every day. You don't see them every day of the winter. You don't even see them every winter. They're not a particularly common type of precipitation, but when you see them, you'll know it. When they're little snowballs, they're soft, but you can crush them with your fingers. Not like slate, not sleet, not like hail. They're soft. That's Graupel. Okay? Graupel actually turns out to be an important thing that goes on inside of thunderstorms. We only have so much time in this course to talk about all this kind of stuff. Graupel is part of the story of how we get the big raindrops and so on, but they, in the winter, might make it to the ground in the form of Graupel or snow pellets. When it's snowing, we want to know how much it's snowing. And that turns out to be a really difficult thing to describe. You could describe like light snow. I mean, you've heard terms like light snow, moderate snow, heavy snow, etc. And it might make sense if you were like talking about it in terms of like how much it's accumulating on the ground, or how fast it's falling, or something like that, or how big the snowflakes are. But that isn't in fact practice how we do it. It turns out that the best way to describe the rate at which snow is falling is to describe it based on the visibility. So if you hear that there's heavy snow in Norfolk, Nebraska, what that means is the visibility is less than a certain amount. I think it's 1/8 of a mile to count it as heavy snow. That way it isn't critical for like how much, what if the ground is warm and the snow is falling but it's hitting the ground and melting? Yeah, that's fine. Or what if it's blowing or whatever? This is mainly oriented around things like airport operations and so on, how much visibility there is. So like if the visibility is better than 1/2 mile, we call it light snow, and if it's between 1/2 mile and 1/8 mile, we call it moderate snow. I don't remember what the exact thresholds are, but it's interesting that it's based on visibility. In part, it's based on visibility because we have good instruments that can measure visibility, and so this can be something that is automated at an unmanned weather station. All those beautiful snowflakes are falling, and they're light and they're fluffy, but Well, yeah, snow is light compared to water. The density of snow is significantly less than the density of water. In general, the ratio that we use to explain how heavy snow is we say that snow is 10 times less dense than water. So like if you have about 10 inches of snow on the ground, that's approximately the equivalent of, in terms of mass, of like 1 inch of rain. You've gotten about the same amount of mass of water from the sky in the form of precipitation if you get 10 inches of snow as you get 1 inch of water. But make no mistake about it, that can vary a lot. I happen to have a map here just sort of to give you a sense. If you look closely on there, you can see that this is actually a climatology of like what is the average ratio of snow to liquid precipitation. But just to give you a sense, down in the south where the snow tends to fall and be very wet and so on, it might be more like 5 inches of snow to 1 inch of water. The snow is heavy and wet. Whereas like up in the mountains where you might have a very dry, fluffy snow, it might be as much as like 40 inches of snow being the same amount of liquid water as 1 inch of rain. It certainly can vary quite a lot. But make no mistake about it, it adds up a lot. The weight of snow, it's easy to have several tons of snow on your driveway. That's why people have heart attacks shoveling their driveway. How often do you spend a day shoveling tons of material? I mean, people have heart attacks and drop dead shoveling the snow. Roofs collapse, things like that. I don't happen to remember. This was a particular event a student sent me where the roof of what is it? It's in Minneapolis, I believe, where the roof of a football stadium collapsed or something. Roofs of Walmarts collapse and so on from the weight of the snow all the time. This is part of the story why deciduous trees lose their leaves, because they know, well, they don't know they're trees, but if the snow were to stick to the leaves of the trees, it would pull the branches down. That they need to lose the leaves before the snow comes. Now, before we go forward with the other types of winter precipitation, let's answer a couple quick questions. Question 1. While it's true that it can snow outside of the meteorological definition of winter, snowfall in those conditions is always just in the form of light flurries. Is that true or false? Make a choice from those two options and get a little feedback before we go on to question 2.